Okay, hello everyone. Welcome to the Abacus tutorial workshop 2. And in this tutorial, we are going to simulate a fire test of a restrained column exposed to the fire. And in this workshop, we are going to perform the structural response analysis using beam element and using cell element. So we have this problem definitions. So here we have a colon, resistant colon. So the colon is made of the uh, uh, this I-beam, which is the test specimen in the middle, and this I-beam in the middle, which is the test specimen, and then it is supported by two steel plate on the top, and then there is this support, the boundary condition or the support applied in the end of the two plate. So this is the fire test conducted by Ollie and Corner. So you can find the detailed information of this fire test in these literatures. So Ollie and Corner tested both axially and rotationally restrained column under fire, and the steel column is made of 127 by 76 UV 13 I profile. The length of the column is 1800 meter. Both end of the column were welded with two two this 200 by 750 into 40 millimeter steel plates. So these are the uh, bottom and the upper steel plate, and these two plate provide rotational restraint in both end of the column. So these are welded and they provide the rotational restraint, and the end of the top and bottom plate were connected to the rig using two light bulbs in each. So the edge restraint can be considered as simply supported, and the imposed stiffness of axial restraint is around 57 kilonewton per millimeter, and on the top of the column the axial load of 205 kilonewton is applied. So in this point column, or maybe here, the load is applied. So the column of the length around 750 millimeters. So this this length, which is shown here in the red, so this is heated, and um, both top and bottom plate are located outside the furnace, which means that these plates are not heated, and the column temperature in the different location are measured using thermocouples. The average column temperature shown in this figure in this figure in the figure in this figure uh, in this figure below is shown, and the average column temperature curve will be used in the structural analysis. So this is the heating due to the fire in this case, and the detail on the test can be seen in Ori and Coron in this reference literature and also in the project documents. Okay, so our task in this model is to create a simulation model using beam element and cell element, and the beam element we create use in the beam element. So the AB is the lower plate and CD is the upper plate, and there is an axial resistance where we need to create the spring axial resistance. There we create the spring, and then we apply the boundary conditions at the end of the this upper and lower plate, and also some boundary condition in the connection between the column and the plate. So first task is to create a beam model as shown in this figure, and the second task is to create the same model using a cell model. So here is the similar model and using beam and the cell element. Okay, and now the structural analysis procedure in Abacus for this type of example is if we are going to add the geometric imperfection in the model, then we have to perform using this approach. So first we create the model as we are going to create the model for the structural analysis, and then we separately perform the linear buckling analysis, and then we write this this node field command at the end of the output request, and then we obtain the desired mode shapes, the buckling shapes uh, for the dynamic analysis, and then we link the imperfection with the result obtained from the buckling analysis. So we will link the result obtained and then finally run the dynamic analysis procedure. So this is the normal procedure in Abacus for the structural analysis using including the imperfections. Okay, all right. And now before making the model, so we always start with the part model in the Abacus, and then the column and the two in plate were modeled as a frame geometry. The column was modeled with a line of 1800 millimeters. This the dimension, this the length of the then the length of the this column, the length of the column is 1800 millimeter, and then the length of this plate is modeled with a line of 750 millimeters, and the cross section dimension was defined in the beam section definitions, and I-beam and the rectangular beam profile were assigned for the column and the in plate respectively. So now we have in part model. So in this tutorial in this tutorial we are going to create different parts. So the lower plate, so this the lower plate we create as one part, we create as one part, and now we create this lower plate as first part, and then also this this colon as second part, and again this upper plate as third part, and this discrete point part as fourth part. So the idea to create this point is to model the spring, uh, axial spring shown over here. So that's the idea 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 here. So we in order to connect the spring between this point and the uh, end of the column point, so we need to create this point that has the inertia properties. So that's why we are creating this as also a part. So we will create a part in that point and assign the inertia properties there. And because we are going to solve this problem with dynamic analysis, explicit dynamic analysis, so we need to have a point that has the inertia properties. Otherwise, it will not uh, simulate that one. So let's begin for the creation of the part. So we will create 4 parts, and then we will follow the dimension of the length of the part, and or similarly we will use this I-beam and the rectangular beam profile for the column and in plates respectively. Okay, so now let's go to the abacus, and in the abacus we have this model here. So now before starting the model, so let's first create the part in the part model. So we can go to the create part option there, and then here we can we can we can name this as the column part. So column colon part, and this is now the modeling space is 3D deformable, and we are going to create using beam part. So, and then this is the planar case, and now we can do this space as the double of the length of the beam, so we can do this as 4000. So then we have this modeling space there. Okay, so now I would like to make a part. So I would like to make a part in a way that I want to have I want to have I want to have this point as 0, 0. So I like to make this in this point, the connection between the colon and the end plate, this point at 0, 0 in my final assembly. So which means that I create the first point of the colon 0, 0, and then this is 0, 1800. And similarly, for the plate, so the total length of the plate is 750. So which means that so which means that uh, 375. So I will go negative 375 0 this point to the positive 375. So I will create a part in this way, and then the length between this point and this discrete point, we create 100 millimeter above these points. So we follow this type of coordinate system, and then create a part, and it will be easy to assemble. So they will be assembled at once. So we didn't need to use this assemble tool in order to model that one, because this part is very simple, and then if you follow this type of technique, then it's easy. And which means that this point will be minus 375 in x direction, and in the y direction it will be the 1800, which is the total height of the column. So we use this approach and then create a part, then it will be easy for us to model in the assemblies. So let's go to Abacus, and now in the Abacus, now we will create a part. So this part, so we start this at 0, 0, and then we need to go to 0 and 1800 with 1800. So we have this one. So now I can click the middle button, and then this is done. Then now we can cancel the procedures and sketch the section for the wire. Yes, so the this beam, the beam for the colon, this colon part is made. So similarly, let's make another part. So let's make this lower plate, lower plate part, lower plate, and this is same modeling space is 3D and deformable wire and planar. So now here we can change the approximate size, because that is 750. So we can make this as maybe 1800 as the sketching size dimensions, and then we first create with the lines, and then first point for the line is 375 negative in x, and then 0. So it will start from here, and then it will go 375 in x positive and 0. So we have this in colon, then we can accept with the middle button, and then cancel the procedures, and then done the sketch. So the lower plate, so we have created the column, and the lower plate is created. And similarly, we can create the upper plate. So let's name as upper plate. We can expand this one, so we have column, upper plate, and it's the same process, and then we the force point is minus 375, and we start in the height of the column 1800. So and then the second, so we are in that point, and then we can now give the another point, which is 375 in x and 1800 in y. So this will give us the second point. Click the middle mouse button, and then down the sketch. So we have now, we create column, we create lower plate, and we have the upper plate. And then we need to create this reference point and assign with the discrete mass and the inertia properties. So in order to do so, we need to create a discrete part. So let's which is 100 millimeter above this point. So 1800 plus 100, 1900 millimeter from this point. So using this information, we can now create another part. So now let's say this is discrete mass. So discrete mass. So let's create discrete mass, and now here this is discrete rigid, not the deformation part. And then we create in the point, not in this, not the other shape, but we create in the point, and then we need to give the coordinates of that point. So now let's give the coordinate of that point, and that point is at 0 0, but in y directions, which is 1800 plus 1, so 1900 millimeters. So then we have the point created there. So we can see here we have this point, and then we can edit that it's point which is created in y direction. So we can apply that one, and under this discrete mass we also, because it is the point created here and it has the discrete mass, it is not there is no any mass defined here. So let's define a mass using this engineering features under this part. We can give the inertia as definition from here. And similarly, this can be done also in the assembly, that in the assembly level also we have different engineering features like crack, spring mass, fasteners, and inertia. But now let's do it in the part module. And then we can go to these engineering features, and then here click on the inertia. So let's leave it as inertia 1, and it is a type point mass inertia. And then we go there, and we can select this point and then accept, and then we give the isotropic mass as some few mass 100 gram. So you define this mass. Okay, so a mass has been defined here. We can see that the inertia has been defined there. Now we have four parts. We have four part there. We have four part there, and now we can go to the assembly, but we have not defined any property, any section definition, or any part there. So let's now uh, first let's go and check one time in the assembly, and then we can see that if everything works. So we can have this all these four parts, and then we can choose this independent. So we will mesh on instance, and then okay, so which means that we have this similar structure. So we keep this point at 0 0, and then we have the these definitions. But now we have not defined any property, so we need to define the property there for each part. Except this discrete mass, we have already defined the mass inertia property for the discrete mass. But now for other part, we have to define the material and also the section properties. Okay, now so the part modeling is completed, and then we go to now in the property model. So in the property model, we will create and define the material properties, and then also we will create and assign beam sections and beam profile for the column and the two lower plate. So now here this column is made the column is made of the I beam. The column is made of the I beam and the in plate, the lower plate and the upper plate. They are made with the rectangular profiles. Rectangular profiles. Okay, so and both this the column, only the column is heated, so therefore we will create the nonlinear materials only for the column, and for the this upper plate and the lower plate we will use the linear materials. So now we first create the this normal nonlinear material with elasticity, plasticity, expansions, and the density Young's modulus, and then we only create this material properties, linear material properties using Young's modulus, density, and the Poisson ratio for the upper plate and the lower plate. So now let's go to the abacus, and then we are in the property model, and then let's collapse this one, and then there is no any material definitions there. Yeah, so we need to create the material, and for the first one we need to create the density, and then the density and elasticity. So here we will create the linear material like that. Then we have this density and the Young's modulus, and then similarly we will create another material, and in the another material, and this nonlinear material. So first steel linear material. So in linear we'll have the density and the elastic properties, and it's not dependent on the temperature. But now on nonlinear material we will create the density, elasticity, which is dependent on the temperatures, and then also we will add the uh, uh, plastic plastic informations plastic information, and also use as a temperature dependent data. And similarly also we need to have the expansion, which is also the temperature data. So we will model the two material like that. But now for the simplicity, we can use the given Python code, and it will generate the material data for us easily. And also you can copy and paste from the input data provided in the description below. But and also the temperature, the amplitude, because of the fire, the average temperature shown in the temperature shown in this one. So this is will be also imported using a Python script. So now we can now move to the property models, and then define the two metal properties. And now we will use a Python code script to generate this data. And now always please remember that you should have the model name model1 in order to apply the Python code, or you need to change the Python code name as the model you have here in the model tree. So now let's go to the file and run the script. So now in that description you can find this colon restrained colon material and temperature Python code. So we can run that one. So it will create a linear and the elastic, this linear material properties. It has been created, and similarly it will create the elasticity, expansion, plastic definitions for us easily. Okay, and also the amplitude, the column temperatures is created here. So the time, simulation time and the amplitude temperature is created there. So in this temperature amplitude curve, so always we use this time span as the total time, so not in the step time but in the total time. So we need to consider that we have this always in total time with that code. Okay, so now we are in the part module, and now first we need to create the sections. So let's create a section, and now the section is the beam sections and type beam. So let's say this is column. So let's say this is column, and we continue, and then we don't have this profile there. So now let's create a profile, and this is the beam column profile, which is the I beam, and then we can continue, and we need to enter the the dimension of the this I beam, and for the dimension we can use these dimensions from the model. So if you import the input file, you can see this I beam. So let's use that one in here. So we have this so we can use that. We can use this. So we have, this is the height of the beam is 120, and this B1 is 76, and then B2 is also 76, and the thickness of the flange is 7.6, and T2 also 7.6, and the wave is 4.2. We use this one, and we say this is the middle, so half of 120, which is 60. So we put this in the middle. Then okay, so we have this column, and now we need to assign the material, which is now for the column we use this nonlinear material, and then also we need to set the temperature input for this one, because we are going to heat that column. So we need to provide that temperature is interpolated from the temperature points. So we have now created the column section. So we can see here a column section is created, and it has the column profile, and the material is still nonlinear. And we can see in the profile manager that this column I profile is created. So similarly, we can also create the rectangular profile 200 by 40 there. So we create this rectangular profile. So let's name it as the plate. So plate. So both the upper and lower plate. So it is a rectangular cross sections, and the height is the this is 200 by 40. So this uh, this is the A is 200 and height is 40. So we create the plate also there, and now we can go to the create sections, and now this is, let's create this as the this as the upper plate. So upper plate, and this is the similar beam sections, and then we select this as a plate profile, and then we select the material as still linear. And now we can leave this default, because we are not going to give the temperature for that one, because it is not exposed in the fire. Only the column is exposed in the fire. Okay, now we have create these two upper plate sections also. Now let's create the lower plate also. So lower plate, and it is similarly the beam, and now we have the same profile for the plate, a rectangular profile, and then the material is linear. So now we accept that one. So which means that we have created three sections: beam for the column, and beam for the lower plate and the upper plate. Now we need to assign these sections. So now let's assign these sections. Now we are in the upper plate part. So now we can change this as upper plate set, So upper plate, this is the set, and then we select that one, accept that one with the middle mouse button, and then we select this is the upper plate, and now okay. So we have create the upper plate, which is upper plate definitions for the geometry, and material is still linear. Yes, so now we can go to the colon part, and then similarly assign, we can name this set as a colon there, and then we can select this part. Now it turns to red, then we can click on the done, and then we colon, so then accept that one. So let's go there. So we have this colon, which is colon and is still nonlinear, and we need to also so we need to go to this lower plate, and here is not, the section has not been assigned, so let's go to assignment and lower plate, then we select this one, done, then we give this the lower plate. Okay, so now we can see here this is lower plate, and it is the part is also lower plate, and there's still nonlinear is defined. And similarly we can check for the upper plate. So this is upper. Now we are in lower plate, so let's change to the upper plate, and then see this upper plate is still linear upper plate region. And similarly on the column, we can also see in the column, so column is still non-linear material is defined. Okay, so we have defined the section and assigned the sections, and also the profile. We have these two profile, eye and rectangle profile. So now we need to assign the orientation of the profile. So now we can we can start with the colon, and then we can assign this one. So we have already clicked the set, so we can click here the set, so colon, and then highlight, so it will highlight the regions, and then continue. So now let's leave it as default, and then accept. So we have the colon created. So let's cancel this one, and then let's go to the assembly now, and now let's view the this beam profile. So in order to do, we need to go to the view, and then there is an assembly display option. So now let's render the beam profile with a scale factor of 1. So we have now okay, so now we have this I-beam created there, not, but we have not assigned this beam assignment for the lower and upper plate, so there is no. So now let's go to the property again, and we have this assign the beam orientation for that one, but not for the lower plate. So let's go to the lower plate, and then have this lower plate assignment, and we can leave it as a default, and then we can accept this one. So dismiss this one. So cancel the procedure, and now we can go to the assembly, and we see that the lower plate is created. Now we can similarly go to the again in the property module, and for the upper plate, and then we go to this assign beam orientation upper plate, and then we continue and accept that one and accept that one. So we can dismiss this procedure, and then we can go to the assembly now. Now this beam is ready, but now our beam orientation is not correct. So not correct. So because we can see in the this model that our beam should be in this way. Now it's in opposite. So now let's change the height of the beam should follow in z directions, but in our model we have this, the height direction is x direction, so we need to change that one to the x direction. So we can change this one with the in the property model. So in the property model we go to the colon, and then we have to have this assign beam orientations, and for the colon we continue that one, and here enter an approximate n1 direction tangent vector as shown here. So what we can do is that we can make it this as 0 0, and then we do this as 1 for the x directions, and we check that one, we accept that one. Now the tangent, this one is our x directions, and now let's okay that one and dismiss, and again cancel the procedure, and then we can go in the assembly model. So now we see that the height direction of the I-beam in Z. So we have successfully modeled the part, and also we have complete the part model, assembly model, and the property model. So we have completed this one, and now in order to this off the render beam profile, so we can off this one, then apply, then we are back to the this uh, beam, or like structure wire structures. Okay, so now now we have finished the part model and the property model and also the assembly model. Now we need to create the step model. So in this model first, we will create this explicit dynamic procedure analysis first, and then we will set up the model setup and analysis and create the output request for this one. And after that, creating the model, then we will also do this buckling one later. But now for one, let's do the same, the explicit dynamic analysis procedures. Okay, and after that we need to go to the interaction module, and then create some constraint and some contact there, because we have different part in the structures. So before now, let's go to the step model first. So in the step model, now we will create these two step. The first step is the mechanical step, and the second step is the heating step. So now let's go to the step model and then create a step. So the first one is the mechanical loading, so we can name it as a mechanical loading step. So mechanical loading step. So now, and this is dynamic explicit type analysis, and then we continue, and then the time period for the 2 seconds we have the mechanical loading step and nonlinear geometry on. Okay, so now let's create the second step, and we can see that here we have created the mechanical loading step, and then create the second step. Now we will create the fire heating step, and now this is the dynamic explicit analysis type. And now for the time period, we will do around, let's do for around 9.4 seconds, around that one. So, and then we accept that one. So we have fire heating and the mechanical loading steps. So let's dismiss this one, and we have this output request, and we have first, sorry, the fire heating and mechanical steps. So now let's say now, okay, now we have first fire heating and the mechanical loading. Okay, now we need to move this one, because the first one is the mechanical loading and second one is the fire. So let's go to the manager, and then we can change that one maybe. Okay, so okay, this is 2, and similarly this is 9.4. Now this is step 1, this is step 2. So let's see that if we can move this. Okay, no, something went wrong. So we need, let's delete this one. Let's delete this one, and we can create again. So now first create the first step is the mechanical loading. mechanical loading step, loading low loading step. So this is the uh, dynamic explicit, and now this is around 2 seconds. Okay, so we have the mechanical loading step, and then again we create the second step, which is fire heating step, and now this is around 9.4. We can do that much. So let's see there. So now it is correct the mechanical step and the firing step, and then we can see in the output request manager that so in the mechanical state created and propagated, and here we can see that what are the quantities that we like to get the output, and let's add also the thermal one, and we can now for this example we only see the displacement. So let's move this remove this stress and strain. Okay, so now let's accept this one, and now we have not defined any this we leave it this as a default definitions, and then we will now go to the interaction module, and the interaction module we have this now this inertia mass, and we need to define a general contact between these all parts, and also we need to tie apply the tie constraint for these parts, this column and the upper plate and also the lower plate, and then also have the spring between these 2 points in the interactions. So now we can go to the assembly here, assembly model here, and then we can create the this we can create the uh, spring there. So in order to create the spring there, so in order to create this spring there, we need to first go to this assembly in the tree, and then go to this spring and dashboards. So now let's leave name as spring there, so let's model name as spring there, and now connection type is connected to 2 points, so we are going to connect this point and this reference point. So continue, and then let's dismiss this one, and now it will ask us to select the first point for the spring dashboard point period 1. So let's select this is our first, and it will now ask select the second point of the spring. Now this is the second point, and we can see that the spring has been assigned there, and now we say done, and it will now ask us the spring stiffness, and we can give the value of the spring stiffness 32,700. So this is the spring value for this problem, and then accept. Then we can see that a spring has been created in this one. So now we need to assign some constraint and define the contact in this problem. Okay, now we are in interaction module, and in the interaction module we create a general contact for the explicit analysis, and we create some constraint to connect the column with upper and lower plate. So let's go to the abacus now. Now here we have this many parts, 1, 2, 3, and 4 parts. So it's better to have some kind of general contact definitions for the explicit analysis, and then also we need to connect this column uh, with this lower plate and also with the upper plate. So now we will first create a general contact for explicit analysis, and then create some constraint, tie constraint in these 2 points. Okay, so now let's go to this create interaction module, and in the create interactions now let's say we have a general contact. So we can name as a general contact there, and for the explicit analysis, and then we create in the initial step, and then we need to give a global property assignment, but we have not created that one, but we can create here the contact types for the global property definition. So let's create contact and then continue, and then have this normal mechanical behavior default. So we have created this contact now, and we select with this include surface peer all, and now we accept. So now here we can see in the manager, in the manager, that this general contact has been created, and also in the interaction property manager we can see that there is a one type of contact definitions, and we can edit this one, but now we leave it as a default. And then we have to now create a constraint, and then we will create a tie constraint between this between this uh, between this surface, so between this surface and the upper surface. So now we create this surface with that node, so therefore we need to partition this edge into two. So let's go back to that one first. So in the in the assembly model, so we are now in the assembly model, and then let's hide this part. So we can hide this column part using this remove selected. So let's select this one first, and then go to this remove selected. So this column is hide. Then now let's create a partitions, and create partition of the edge, and now we click in the middle point of the selected edge. So we have selected this edge, and now in the middle we select, then partition definition complete. So we accept that, and this uh, this plate is divided into two part, and we have one point created there. And similarly we need to create for the down part also. So now we select the edge for the partitions, and then we select the middle point, and then we create the partition. So we have now created the partition of the edge, and it has now these two parts in the lower and upper plate. So now let's replace all. So now we are back, it will show this all, and then we can go to the interaction model again, and then now we need to create a tie constraint. So constraint 1 we can leave it as this for the upper part. So constraint 1 type tie, then we continue, and then select a masters. Then so for the master, let's select the surface as a master surface, and then we select this one. We can leave it this as default definition. So and then we now done, and it will ask which surface type. So we choose this yellow there, in yellow, and then the slab. So for the slab we will choose the node regions, and then we will hide this this part. So so select it hide, and then we will select this node regions, and then we accept that one. And then we have this created a constant one with tie, and define the master surface and the slab surface, and then this we give the position tolerance. So the tolerance around 5 millimeters, so around this 5 millimeter. So we give the tolerance of that one, and then we accept this one, and then we have this tie constraint between this and this node. So okay, so now similarly we create for the down part also. So let's create tie constraint 2, and then continue, and select a surface for the master type. So we have selected this surface, and then we accept it, and then choose this in magenta, And then now we need to change the slab type node regions, and let's hide this one. So let's hide that selected, and then click on the node and done. So similar also here, the position tolerance we define as a 5 mm and leave everything default. And back to all. So we have now created general contact for the explicit analysis, and then we have also connect this part together with the tie constants. Okay, so the interaction module is finished, and now let's go to the mechanical module, mechanical load module. So in the load module, we will create the mechanical load, and also we will create the boundary conditions, and then we will define the initial temperature and the temperature due to fire in this step. So let's go to now Abacus here, and then in the load module, so now we have this structure there, and first we will create a load, and this column is loaded in the connection between the uh, top of the column and the upper plate. So in this point, so we create a load there. So we say okay, the mechanical load, mechanical make mechanical load. So and the mechanical load is created in the mechanical steps, and it's the type is the concentration force. We create this concentration force, and then we continue there, and we okay, we can name this as this set as load point. We can say this as a load point, and then we can select this point, then accept, and then in the load point we follow this global Cartesian coordinate systems, and then we have this similar XYZ system. So the force is applied 205 kilonewton force is applied there. So but in negative y direction, so let's have 205, and so 205 kilonewton force is applied there, and then the amplitude, so the amplitude should follow the loading curve. It should follow the loading curve as shown in this structural analysis procedure. So we have this first step. In the first step, we have increased the loading from 0 to maximum 1, and from this in the second step, which is the fire step, we keep it is constant. And similarly we do same for the temperature. So in the first step, we only apply the initial temperature, which is 20 degree, and then apply the temperature due to fire. Okay, so now let's move to the abacus. So we need to create the loading curve, and we can create the loading curve using amplitude. So let's name it as a loading curve. So loading curve and loading curve, and we choose the tabular as a type, and then continue, and then we change this time span as a total time, and we start from 0 0, and at 2 we have this at 2 uh, we have one maximum, and then similarly we insert one row, and then at 11.4 we have one, so it is kept constant, and then we change the amplitude with the loading curve and accept that one. Okay, and we go to now in the step model, and see that okay, the total time is 2 plus 9.4, which is 11.4. So that's why we have defined this loading curve in that way. Okay, okay, so now we go back to the load module, and a concentration force in this point has been created, and now we need to create the now boundary condition. So let's create the boundary condition 1. So the boundary condition, let's create this the in upper column. So upper column, in the upper column point here, so let's create this one in the initial step. So in the initial step, and the category is mechanical, the type of is the displacement and rotation. So let's create that one, and we can also name this set as upper upper colon point colon. So upper colon, and then we can select that one and accept, and then we have these boundary condition definitions, and we need to define the this boundary condition. So we fix in x direction, so it doesn't move in x direction, but it can move in y direction and not in z direction. And also we fix the rotation around uh, this y direction also, we fix that one, and then we accept. So one constraint is created there, and similarly we need to create also on the lower column. So let's create, and we name this as uh, lower colon point, so lower colon, and also it is in the initial, and we select. So now let's name the set also as lower colon, and then okay, there is a spelling mistake, lower colon, and now we select the lower colon and then accept, and the boundary condition is that we fix this, and all the translation degree of freedom and one rotational degree are true. Okay, so now we can accept this one. So we have created the we have created two boundary conditions, and now let's create one more boundary condition for the lower lower plate, and we create for these 2 points. So as a simply supported boundary condition, so let's have that one, and which is now this is lower plate left and right side. So left and right, so we can name it as left and right, and then continue, and then so maybe lower, we can name it the set as also same lower plate left and right. So we have that one, and let's select this one first and the right. So accept that one, and we have this we restrain this, it can move in x direction but not in y and z, and then leave the this uh, translation degree of freedom as it is. Okay, so now for the initial loading step, so we have apply this uh, 3 for the colon and the end, and and now we need to create this extra two extra two uh, boundary support in the fiery steps. Okay, so in the fiery steps, so let's first create in the spring node here, and then also we will create the upper plate left and right. So the idea here is that we apply different boundary condition in mechanical step and heating step to avoid the axial restraint during mechanical loading steps. So in the mechanical step, the displacement rotation boundary condition were applied in lower in colon where and the colon top end, and also the color lower end, and respectively. And then also in the heating step, two additional boundary conditions were imposed at the discrete point node, which means in this uh, reaction reference point in this point, and the in part of the upper plate, so here. So now let's create this two. So now let's name this as a spring node. So let's name as a spring node, and this is also created in the fire step, and now it's the category displacement and rotations, and then we can say this is also the spring node sets, and then we can choose that one and accept, and then we will have to define the we have to define this all fixed xyz, and it is allowed to have all the rotation. Then we accept that one, And the last one for the upper plate, upper plate left and right. We need to have that uh, displacement and rotation boundary conditions, and then we can name this also as upper plate left and right. We can name this as, and then we can select these two part. Okay, we have selected and then accept, and here we will have that we will have this it can move in x direction but not in y and z, so simply supported boundary conditions, so we accept that one. And then the this loading and the boundary condition for the structure has been defined, and now we need to define the initial temperature and the temperature due to fire here, and that one we define using predefined field, and here is the place to create a predefined field. So now we will first define initial temp, which is initial temperature, and that is defined in the initial step, and it is the temperatures. So now we need to select the sets. So now we have these sets. So before that one, let's create the node for that one, node set. So before doing that one, let's go to in the low mesh module there, and then we will create the mesh there. So we have this. Now let's see this one, and then we select this all part, and then after that we select okay, the approximate global size 25 mm. Okay, and then we can also now select this element type, and the element type is the explicit beam, so B31 or two node linear beam in space. We accept this one, and then let's cancel these procedures, and now we can mesh the part, so mesh the part and done. So the we have this mesh statistics, so we can also cross check that the mesh okay display on the report, and it has 132 linear line element of type B31, and total number of node 135, and total number of element 132. Okay, so we have now created the mesh. So now we go to the assembly, and then we create a set of all nodes and the nodes which are exposed in the heat zone. So now we can visualize these nodes there, and then now let's first create the all node set. So let's create a set, and this is all nodes, and then we select the type, and then select all the node with this. So we click the left mouse button and drag over the area, and then it is selected all, and then done. So all node is selected there, and similarly now let's create the heat zone node. So heat zone node, and only 1750 millimeter of the column was heated, so there is a space 25 mm up and left, so that's why we have created the minimum the approximate size of the element 25. So now we can select from this node and continuously select all the node and then select up to the button. So we have now this heat zone selected, and then accept that one. So now we can this so we have this all node and the heat zone. So this is the place where we apply fire. So now we have created these two sets, and then we can go to the loads in module, and then go create the predefined field, and now we will create the initial temperature field, and this is in the initial step, and the type of category is the temperature, and then we will click in the set, and here in the all node we can highlight that one all nodes, and then continue there, and yeah, it is the distribution is direct distribution, and section varies constant through the sections, and this is 20 degrees Celsius. So the temperature has been assigned, and then you can see this type of uh, symbol that it has been assigned. Similarly, so we need to define fire heating. So fire heating, and then after that it is created in the fire step, and the type is temperature. And now we need to select the heat zone nodes, and then it is also constant through the region, and then we have to, for now, the magnitude 1, and it should be multiplied with the reference amplitude curve, which is the column temperature. So now we accept that one, and it has been defined. But before doing this one, so we need to make sure in the property model that so we need to go to in the property model, and we check that the colon, so the colon is now interpreted through the temperature points. But now we like to have this linear by gradient because we have not specified the temperature in the temperature point. So let's change to linear by gradient, and then okay, so we can check this one also. Okay, this is now okay, linear by gradient, and check for the upper plate also, it is also same. So now that's okay, and we have now create the loads and apply the temperature and the initial temperature, and also the temperature due to fire. And now we have this, we go to this mesh, and then we can now see if the job run or not. So now we can so we have model this all part together, and then now let's go to the job module. So in the job module, uh, so in the we have finished this also, the mesh model also, and in the job model, so we will need to create the input file, uh, and also we need to create the edit the input file, and also add imperfections, and and then run the explicit analysis first. So to add the imperfections, so we need to have this buckling analysis before, and then we link the result from the buckling analysis to the dynamic analysis. Okay, so now, and then we will visualize the process. So let's go to Abacus now. In the Abacus, we have created the model. So now what we can do is that we can copy this model. So let's copy the model, and then let's make this as a buckling, buckling. Uh, so buckle. So let's say this structural 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 beam buckle. So buckle, so we can name this as a structural beam buckle, so we can accept that once, and then also copy this model, and then so simply remove this, which is now structural analysis of the beam. Okay, so now we leave this as it is, and we just copy these two model, and now we can now we can change, now we can run and make the input file for these two models. So now let's create these two input file for the buckling, and also for the this structural analysis. So first let's go to this buckling, and then we need to create, now we need to change the step for this one. So let's go to the step manager, and then this is now the dynamic explicit procedure, so this should be changed. So we can delete this one, so let's delete this one, and also delete this mechanical loading step also. Now we only have this initial step, and now we can create this buckling, so buckling step, and under this linear perturbation analysis, then we can say this step as buckle step. So we can now create the buckle step, and then we can choose as a default eigensolver, and then we will request this three number of the eigenvalues requested, and then we accept. So it says that interaction cannot be used with the current procedures. Okay, so now here we need to go to these interactions and then suppress that one. So we have now suppressed these general contacts definitions. So now we again go to this step and then create this buckling step. So linear permutation buckle, and we name it as a buckle step, and then continues, and then we will extract three eigenvalues and then we accept. So the buckling step is uh, created. So now we can just create a new job. So let's say this is similar name as structural beam buckle. So and then now we continue and we accept as it is, and now we have this buckling, and then let's submit that job in the job manager. So it has been submitted and we can see the status if it is if it will work or not. It says that the differential stiffness matrix is complete. Now the eigensolver cannot be solved in a looking at the most likely cause that non-zero loading pattern was not. Okay, so we have now some we have not defined the loading in the buckling steps, so we need to create also the load. So let's go to the load module, and then let's create a load here. So we can name this as load 1, and at the load point we can select the geometry, and then let's have this -1. So the loading is applied, and now we can go to the job in the job manager and then again submit the file. So we need to define some unit load there to run the buckling analysis, and now it is we can monitor that one, and now uh, so this job is now completed. Okay, so it has completed, and now we can see the results, and now yeah, we have this first buckling shape, so which is like that, and then the second buckling shape in that way, and third in that way. Okay, so usually we have this first one is this first buckling shape. So let's it will buckle in this way, and the second one might buckle in that other way and in this way also. So we have different buckling shapes. So we add these three modes, or maybe only one mode is sufficient for us. And now we need to edit this this result file. So we need to go to our uh, our 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 input file. So in the working directory, in the resting colon here, you can see that this is the working directory, and here we have this buckling input file, and then we need to edit this one. So let's edit with the notepad there, and then here we have this all definition. So we go directly to the down, and before that one here we will write this node field you to write the buckling shapes. So now so we will create uh, this we will write that one, so it will write these three uh, nodes for us, and then we save this one. So this structural beam buckle, this there is an input file for this one, so we have created the input file for the buckling analysis. Okay, so now let's go to the abacus, and then now let's run the job from the input file. So now let's create this job again, and then we say okay, let's write this input file, because input file input. So let's say let's write in from the input file we are doing this structural structural this input buck we can name this as input beam buckle. So beam buckle, we can name this file name as input beam buckle, and now this is from input file, and then we have this structural beam buckle input file. Then we continue, and okay, so we have now created this from the input file, not from the models from the Abacus CA, but from the input file. And in the input file what we have done is that the structural beam buckle.inp is the input file, so we have add these ones node field u, so it will get those uh, modes buckling mode saves in the result file. Okay, so now we can now also run this one, this input buckle, so we can submit this job and then also run the job. Okay, now it's running, and then it will finish fast, quite fast, and then we can see that it will write the field file for us. So we can see that okay, so it has written this input beam buckle ODB file. Okay, that's all right. Now then we move to the this. Now let's create the another job, and it is from the structural beam. So let's say this is also input. Now we leave it as the structural beam because we need to first create the input file for that one. So let's name it as structural beam. Okay, so and then now I like to change. Okay, we can leave as a default. Okay, and then here is a structural beam, and then we now do a data check there, and if everything is fine, then we write the input file, or maybe it will write the input file when we when we do the data check. Okay, yes, so it has written the input file already for the structural beam when we have done this data checks. So now the check is completed, so now we have this structural dot beam inp. So we will open this one with notepad, and then before before the step so before the step so we go down there, and step before the step we will have to include the so before these mechanical steps, so we will here include the imperfections, and then we can just copy this one imperfections as it is here. So this is the mode saves, and they are the this related uh, factor, and the correct factor for this type of imperfection can be obtained with the sensitivity analysis, but now we assume this one as the value for this tutorial. And now here we need to change the name of the file of the buckling file, and now with the buckling file is now the name is that it's input beam buckle, so we need to write input and then beam and then buckle. So that's the name of the file. So here is the name, input beam buckle is the name of the input file. And from okay, so we have that also, and yes, that's the name of the result file, and we have already run this buckling analysis, and now we in this step, and we have added, and then we can save this one, and then the structural beam. So now we go again, create a job there, and now we create from the input file. So let's name as input, then the structural beam. So and it is from the input file, and we give this structural beam, which is the input file, and then we continue, and now we will use this parallelization, use multiple CPUs there, and then we accept this one, and then now we can submit the analysis. So let's now submit it and then wait for the result. So this might take little time for the solutions, but let us confirm that it is running, so we can now monitor there. And then if everything doesn't start, then okay, now let's kill this one, because now it will. Okay, so now we can see if everything is running as it is, and then we can stop. But now I think we have very less output in this one, so the result might not be that good, but we can change that also. So now if we go to this structural beam, and if we go to this step, and if we see that the here, so in the output request, it is in 20 interval, so it will have these 20 points in the analysis, but we can change that to 0.01 time. Okay, and but now here we need to go to the job manager, and we see that this is running. But now let's kill this one. Okay, and it has been killed, and let's dismiss this one. And then now we need to this this one, we need to make the input file there. So structural beam is structural beam, so now it will, now let's write the input, and it says that there is already structural beam. Yes, would you like to overwrite? Yes, I like to overwrite that one. And then we can go to this. Yes, so this imperfection will go away, and then we can see that here the output is requested the at interval 0.1. So, and yes, it is this interval 0.1 output field requested in this one. And we have not also requested the temperature, so we can also add the temperature there. So let's also add the temperature in the step. So we will go there, and then we done. Okay, we have this thermal. Okay, there is interval, so we can say this is at maybe exact time, even more good. Okay, dismiss, and then we need to go again in the job, and then let's write the input file again. Yes, and then we can open this. Yes, so now input file. Yes, and now we have the input file, temperature also, and now we need to, before this dynamic analysis, before that one, we need to apply these imperfections. So now let's add that imperfections before this step. So let's click and then add the imperfection there, and then we save this one, and we have saved this. And then we can go to the job, this input file from the structural analysis. We can make a little wider this one, and this is a structural beam INP, and it has been terminated. But now we can submit, and there is already job file exist for the input structural beam. But okay, to overwrite, yes, we can okay that to overwrite. And then now it has been submitted, the job, and we need to wait for some time, and I will come back after the job has been finished. But now it says the aborted there, but let's say what is things. So Okay, so we don't have that result file there written. So now we need to go back in the input file and change that one. So this is good practice in this tutorial, that we do mistakes and also learn from the mistakes. So here the file name is missing there, so we have to name this as input buckle beam buckle. So that was the buckling analysis for this one. So this is the job, and we have now the correct name. Yes, and then we can save this one. Let's save. Okay, let's save this one, and then and now go back and then again submit this job. So here we will submit this one and check if it is running or not. So it's good to make some mistakes and know what is the problem, so we can know that all the time the input file doesn't work and something we miss something. Now let's monitor this one, and now it has completed the analysis input file processor, and it has started the Abacus explicit package in the solutions. And then if the increment start working, then we can pause the video. So let's see if it start working. So yes, now the Abacus explicit has been started. So and now it should start solving, and then we can see also the output request for here. It will what is the current status of the ODB written for that one, and if we have some error we can see there. And then here is the data files where it shows okay, the first increment as first step has been started for the time 0.1, and also it has write this ODB output written for the step 1 frame 0. So now it will take some time to finish this one, and we will come back after that. So now the simulation has been completed, and now we can go to the we can go to the visualization model, and in the visualization model we will post process the structural analysis results. And here is an examples from the previous analysis that for different yield strength and the response of the structures. Okay, so now we will plot the lateral displacement of mid-span of the column and also the axial displacement of the column. So we will try to plot these two in the post-processing and see the results. So now we can go to the Abacus, and now we can click on the result. So now the result has been obtained. We can see the deformation counter here, and also the plot. So let's hide this spring. Let's hide this spring, and also let's have this in non-uniform. Let's say in x direction we have this fireband in 100. So we have this. So we can see this is the deform shape, and maybe not 5 but 3 here should be okay, and here should be 50. So now we have this deformation scales there. So now we can animate this. We can animate the time history. So now we can see that the simulation, the animation of the column. So yes, now we have finished the pre-processing. Sorry, we have finished the solving. Now we can plot the axial displacement in these directions, and also the axial force lateral displacement in here in the column, how much versus the temperature, and also the axial displacement of the column in this point. So now we can go to the plot there, and then plot from ODB field output history. So now we can choose the under the position you can choose the unique nodal, and then we can select the temperature and also the displacement U1 and U2. And similarly we can now click the node. So let's click this node first, and also this node. So now we can select this two node is selected and then save yes, and this XY data has been there. So we can see at this 30 node. So this is the lateral displacement of the beam. So this is similar to this response, which is the lateral displacement of mid-span of the column. And similarly we can also see the axial displacement of axial displacement of the of the column also. So we can now we can plot this in the temperature and what's in not in time but in temperature. So we can now this operate on XY data continue, and there is a command which is called combine. Which is called combine. So let's use this combine post processing in Abacus. So combine, then we have to give the x value, which is the temperature. Here we can select this temperature and then comma and then this u2 value. So we can select this one and save as and then accept that one, and we can see this plot. So here is the plot of the plot which looks like which look like this axial displacement of the column. So similar to that one, and so in this way we can post process the results, and this is the end of the tutorial for the restrained column using beam element. Thank you.